previous lecture, I made an assertion that was in error. I said that if I measure the mass of a thing, I have some kind of scalar balance, gravitational, electrical balance, whatever, I do something a little bit more clever, and I measure the mass of an object. I measure its mass, and I measure its mass, and I measure its mass in successive experiments in different contexts, and I find that the mass is always the same. I also mentioned in an introduction lecture that there are two different ways, really, of measuring the mass by comparing the mass of an object to its weight under the force of gravity, or also potentially putting a mass on a spring and letting it oscillate and comparing a mass to the inertia of the thing, with mass ultimately being a measure of the inertia. In every context that I do it, the mass is the mass is the mass is the mass. And so when calculating the kinetic energy and I perform an integral, I brought the mass out of the integral and said, well, you know, the mass doesn't depend on this integral of velocity, and so I can bring it out. It turns out that's erroneous, because if I do an experiment, it would have to be an extraordinarily clever experiment. Imagine that this is the result that I get, because this is what I would find. If I measure the mass of an object by putting it on some sort of balance, and I just set it here in front of me and I read what the scale says, that would be a mass that I measure when I'm at rest with respect to the object. That is, the object's not moving. And so I'll call that mass, I have to give it a special name, and I'll give it one that's sort of very familiar to us. I'll call it m naught. So here's my graph of the mass as a function of velocity, because what I'm going to do, and imagine it's a tricky sort of experiment to build. But I built some kind of apparatus where I can measure the mass again, except measure the mass of the object as it moves by with a velocity v. You can see how comical this is. Imagine me running along with a pan balance, measuring the mass of a thing as it moves by with a velocity v. Well, if I run along with the thing on a pan balance, it still has a velocity of 0 relative to me, so I'm still measuring the same thing. So what I have to do is I have to make a measurement of the mass of a thing as it goes zooming by. Tricky to do, and perhaps difficult for you to imagine a way that you could do that, but it can be done. For example, I could use electric fields and the object could have a charge, and then I could apply a force sort of remotely as I observe it move by, and I can measure the acceleration, and the mass is in proportion to the acceleration. I can do that experiment. And so imagine that I've done this experiment and I measure the mass as a function of velocity, and you would expect that I get the same mass every time, because the mass is the mass is the mass. It's not so. What I find is that as the velocity of the object increases, my measurement of its mass increases as a function of velocity. And I get a graph that looks something like this. In fact, the faster it goes, the more radically its velocity increases. It's quite a remarkable experimental result. And I find, as I push my luck with this experiment, that the behavior is asymptotic. And the speed that is the asymptote of this behavior is the speed of light, which naturally I think we're all aware I denote as c. 3 times 10 to the 8th meters per second. A fantastic velocity indeed. So as absurd as this experiment is, for you to imagine some sort of apparatus that we have here in the classroom where we could do this, the fact that the speed of light is such a very, very large number means that at slow speeds on this end of the graph, as I do the experiment, I would not find that the mass changes very much. You might wonder about the nature of that curve. Well, what I'm going to do is I'm going to use some kind of software and import my data and find out what the functional form of that is by doing some curve fitting. So this is an empirical result that I'm getting here. And what I discover is that the mass that I measured, which I'm going to call m, is actually just proportional to the mass that I measure at rest, calling the rest mass, as 1 over the square root of 1 minus the speed squared divided by c squared. See, I just do some form fitting and I find out, or some functional fitting, I find out what that curve is. And it turns out the best mathematical fit that I have is that function. Infinitely massive. Yeah, it is pretty weird. But it's an experimental result. This is the natural behavior. You can't deny, you make up a fanciful thing and say, well, that's your logic and reasoning I think is flawed there. But if I make an observation and I make measurements and I draw a conclusion that's within the uncertainty of the measurements, it's undeniable. This is the reality of what would happen if I did that experiment. And so what I find is that the mass is not constant with respect to velocity, but in fact is a function of velocity like this. This quantity, 1 over 1 minus v squared over c squared, is called the Lorentz factor, named after the mathematician who first conceived of it, and is often given the symbol gamma. And so we write this as the mass of the object is equal to gamma m naught. Notice that if gamma is 1 over the square root of 1 minus v squared over c squared, v squared over c squared is going to be a number less than 1, so the denominator here is going to be slightly less than 1 most of the time. And so the mass that I measure is always going to be greater than the rest mass. That is, the rest mass is the smallest value that I will measure for the mass, making a measurement of the mass when the mass is at rest relative to me. So this observational fact that I make, that I had to do a sophisticated experiment to get that, shows me that I made a mistake in calculating the kinetic energy. My kinetic energy is wrong because as I derived an equation for the kinetic energy, I made the statement out loud, the mass does not depend on velocity, so it comes out of the integral. No, it does not. And so what I'm going to do is correct my previous lecture by deriving the kinetic energy again, doing the same argument again, but not allowing myself to draw the mass out of the integral. So here I go. The work energy theorem tells me that the work done on a particle, which for today's discussion, I'm going to assume that the particle starts from rest and is accelerated by the force, that the work done on the particle is equal to the change in the kinetic energy. Naturally, the change in kinetic energy is the final kinetic energy minus the initial kinetic energy. Particle starts at rest, presumably its initial kinetic energy is 0. So the work done is simply equal to the kinetic energy. So the kinetic energy is equal to how I have defined work. And at the end of the previous lecture, I had defined the most general form of the work as being the integral of the force dotted into the displacement. This is the most general way that I can write the expression for the work. I don't need it to be this fancy because I'm going to more simplify the argument and say that I exert the force entirely in the direction of the x-axis and that the particle displaces itself entirely in the direction of the x-axis. So F dot dr, which is F times dr times the cosine of the angle between them, quite simply just becomes the integral of the force times dx. It's no longer a vector equation, and it's simply a force in the direction of the displacement integrated to find it. Well, to proceed with that, the very first thing, the same thing that I did in the previous argument, was that I'll replace the force with what I know the force to be equal to, which is the mass times the acceleration times dx. And this is the integral that I want to solve, and I know that this is the integral that results in the kinetic energy. Because I see the kinetic energy is going to be equal to this, I simply need to find it. So here, I'll now write this as the integral of the mass times what I know the acceleration to be equal to by definition, dv dt, dx. Now, in order to proceed here in the most convenient way possible, I'm going to introduce a concept that we have not yet encountered in our physics, and that is the momentum. If I were to go back and read what Newton had to say about motion, you would find that he was not so much interested in the acceleration, but in changes in what he called the quantity of motion, because he understood that the motion of an object depended not only on its velocity, but also on its mass as well. So Newton goes on about changes in the quantity of motion due to a force impressed upon an object. Well, the quantity of motion that Newton referred to was the momentum, which is given the symbol p, and for our purposes, quite simply, is just the mass times the velocity. So I'm going to introduce the momentum now just for the compactness of my notation. It's not a requirement, but it's more, I guess you could say, it's more stylish. So here I have the mass times dv dt, and you might say, well, go ahead and take the mass out of the integral. I cannot do that, because the mass itself now contains velocity. And I'm going to turn this into an integral of velocity, and when I do, I'm going to have to keep the mass in there. So what I'm going to do instead is I'm going to take the mass inside the derivative. So what this becomes is the integral of dmv. I don't like writing those parentheses, but I'm trying to be as clear in my notation as possible, dx. Well, I recognize what that is. That is the integral of the derivative of the momentum with respect to time times dx. And that's the integral that I'd like to solve. Well, I'm continuing to work on this integral as I go at any rate. Realizing once again, keeping always in mind that I'm solving for k, the kinetic energy here, it's the integral of the derivative of the momentum with respect to time times dx. I'm going to do a little bit of chain rule. I'm going to introduce dv into the expression, which I could certainly do according to the chain rule anytime that I like. I'm going to make dp dv times dv dt dx. And you know that I'm at liberty to do that because the expression that I had previously here is equivalent to this one, because the dv's would cancel and it becomes exactly the same thing. Doing a trick that I did the first time I took the derivative of the kinetic energy, I'm going to move the dt over here so it's underneath the dx. And so what I have is the integral of dp dv dv dx dt. I've simply moved the dt under the dx. Well, dx dt I recognize is the velocity. And so ultimately the integral that I'm trying to solve is becoming this, the integral of the derivative of the momentum with respect to velocity multiplied by the velocity multiplied by dv. I've simply rearranged terms. I cannot perform this integral for a very simple reason. I don't know what dp dv is. So I have to pause at this point. I have to pause and compute what dp dv is. Or I guess just find out if I can compute what that is. And once I compute what dp dv is, then I'll come back to this integral and then continue on and see what happens. So this integral, pause. And over here, I'll try to calculate what dp dv is so I can come back with it. dp dv obviously is going to be the derivative with respect to v of the mass times the velocity, because that's what momentum is, mass times velocity. But not just the mass, this mass, which is itself velocity dependent. So you find that the derivative that I have to do here is a little bit more sophisticated. This is the derivative with respect to velocity of the velocity, well, I should write that, the rest mass times the velocity divided by the square root of 1 minus the velocity squared divided by c squared. It's a daunting derivative to take because I have velocity in the numerator, I have velocity in the denominator. It's a bit much. It is made easier if I look at it as the product of two functions. So the derivative with respect to velocity of the product of two functions. So I'll put a bracket here. The first function is m naught times v, and the second function is 1 minus v squared over c squared to the minus 1/2 power. So this derivative I'm taking is the product of two functions, and so naturally I'll apply the product rule to its solution. So back over here, again, realizing that what I'm solving for is the derivative of the momentum with respect to velocity, simply reiterating that, is going to be the derivative of that monstrosity. So applying the product rule of differentiation, I'll take the derivative of the first times the second plus the derivative of the second times the first. And we'll see what that gets me. The derivative of the first is simple. The derivative of m naught v with respect to v is simply m naught. And the multiplied by the second, which is obviously just 1 minus v squared over c squared. That part quite simple to compute to the negative 1/2 power. Plus, now things get a little squirrely because it's going to be m naught v, the first, multiplied by the derivative of the second. Well, the derivative of the second is going to be equal to negative 1/2 1 minus v squared divided by c squared to the negative 3/2 power. I'm not done yet. For those of you who know your calculus, I'm just pausing for a second to let everybody catch their breath. All I did was I took this big term here and I took the exponent down and multiplied it and demoted the exponent. So a negative 1/2 came down in front, and then I have this raised to the exponent demoted by 1. But I'm not done yet. That has to be multiplied by the derivative of the inside. It has to be multiplied by the derivative of 1 minus v squared over c squared with respect to v. Well, the derivative of 1 with respect to v is 0. The derivative of v squared over c squared with respect to v is 2v over c squared. So what I have to multiply here is a negative 2v over c squared. Well, things have become quite naughty indeed, but it's okay. I can compact this down quite a bit. Do you see that I have a negative 2 here in the form, well, negative 1/2 here, and I have a negative 2 over here. So that negative 1/2 completely cancels the negative 2 there, right? And so now what I'm left with, and do you see that I have a v here and a v here? So I'm going to try and clean this up the best that I can and write it, because I'm running out of space on the board. It's a little bit of a large derivation here, but hopefully I can do it. Takes a little bit of good management. dp dv is equal to m naught over the square root of 1 minus, you know what, I'm not going to write that as a square root because I'm going to combine fractions and it'll be easier to see if I don't do it that way, over 1 minus v squared over c squared to the 1/2 power, right, because I've taken that from being in the numerator to the denominator, plus what I have left over here. Now, this is m naught v, and there's another v over there, so it's m naught blah, 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 v squared over c squared divided by 1 minus v squared over c squared to the 3/2 power. I want to combine these two fractions, and that means finding the common denominator of these two. It's actually quite simple. All I have to do is multiply the numerator and the denominator of this by 1 minus v squared over c squared, because then this denominator here will be multiplied by 1 minus v squared over c squared to the 2/2. And when I multiply them, I simply add the exponents. 2/2 plus 1/2 is 3/2, and then I have the match. So I have to take this first term and multiply the numerator and the denominator by 1 minus v squared over c squared. So I'll do that and combine these fractions. And when I do, I get a pleasing result. It doesn't look like it at first, but what I get is m naught minus m naught v squared over c squared plus m naught v squared over c squared divided by 1 minus v squared over c squared to the 3/2 power. That, of course, is pleasing because in the numerator I have minus m naught v squared c squared plus m naught v squared c squared, and so those will cancel each other out. And I'm left with my final result for the momentum, which regrettably I don't have any room to write, so I'm just going to take it up to the integral and write it there. But the derivative of the momentum with respect to velocity is clearly m naught divided by the quantity 1 minus v squared over c squared to the 3/2 power. Going back to where I'd paused my integral, all of what was just happening here happened because I made the argument I can't evaluate this integral unless I know what dp dv is equal to. Well, now I know because I've computed it. Taking that dp dv and plugging it back into this equation, I get that this is equal to the integral of m naught v over 1 minus v squared over c squared to the 3/2 power dv. Which without question, is a challenging integral to solve, but one that with an introductory course in calculus we can solve. But I don't like it, it upsets me. What upsets me? You upset me, you crazy denominator lunatic thing. Okay, fine. Am I okay?
Oh, yeah.
This is the problem. So, u is equal to, I'm going to choose, choose u, is 1 minus v squared over c squared. And so I immediately compute du dv. Du dv is already familiar, I've already done that once, is 2v over c squared. And I see that this choice was excellent because as a result of this choice, I can replace dv, solving this for dv, with negative 1/2 c squared over v du. I can make that replacement in the integral. You have to forgive me for how complicated this is. Well, not complicated, but how much real estate I have to use in order to make this demonstration. So I'll make that substitution in my integral. A very pleasing thing happens. Do you see that my dv has a v in the denominator of it? It's c squared over v. That v will cancel the v in the numerator, which is quite helpful indeed. So I'll have a negative 1/2 m naught and a c squared. I'm going to go ahead and pull that out of the integral to really make things clear. Recall that what I'm calculating here is k, the kinetic energy. So I'll write here k equals to sort of reaffirm that that's where my integral is going. Negative m naught c squared divided by 2, the integral of 1 over u to the 3/2 power du. And so once again, I've taken an integral that was challenging to solve, and I've made a good substitution that turns it into an integral that I can easily solve.
How are you because it's an initial, so it's a constant.
Right. What is the integral of 1 over u to the 3/2 power? Negative 2 u to the negative 1/2. Excellent. Well done. So it's negative m naught c squared over 2, negative 2 u to the negative 1/2 power. Well, I have to substitute my u back in again, but I just wanted to show that that in fact was what it was. Notice how there's a negative 2 on the inside again, which cancels once again the negative 2 on the outside. And what I'm left with is m naught c squared times u to the 1/2. That's 1 over the square root of 1 minus v squared divided by c squared. Limits of integration. Evaluating this from 0 to v. Recall that an assumption that I made earlier on, right here at the beginning, is that delta k was equal to k, which implies that the initial kinetic energy is equal to 0, which implies that initially there is no motion, which certainly means that the initial velocity is equal to 0. So evaluating those limits, the kinetic energy becomes equal to m naught c squared multiplied by this thing evaluated at v, which is 1 over the square root of 1 minus v squared over c squared, which I call gamma. I wonder if you'll mind, please, if I just write gamma. And this thing, minus, this thing evaluated at 0. Well, when v is equal to 0, this is 1 over 1 is 1. So evaluated velocity of 0, that is 1. And so my final result is that the kinetic energy of an object is not 1/2 mv squared. Is not what I imagined it to be, but is in fact equal to gamma m naught c squared minus m naught c squared, which is a rather remarkable thing, because my original version of the kinetic energy, realizing that I'm describing an energy that depends on motion, is 1/2 mv squared. It depends on motion. That's great, but this energy, no. This energy has a part that does not depend on motion. It's a constant. Particle has a quantity of energy by virtue of its very existence. And by the way, since c squared is a very, very large number indeed, there's a large amount of energy. It's a fantastic amount of energy. It's a fantastic amount of energy, which we'll comment on. We'll give it a name. I'm going to call it E naught, the rest energy. So what I'm interested in computing, now that I know the true value for the kinetic energy, is what would be the total mechanical energy of a particle. Now, a thing that we haven't discussed yet is potential energy. I've said that there are a profusion of potential energies. We know that there's an energy associated with the configuration of a system in space. We just haven't discussed it at length yet. Let me imagine for the moment that there are no potential energies, and I'd like to write the total mechanical energy. The total mechanical energy, E, of the particle then is simply the kinetic energy. But now I realize that that energy also includes an unction of rest energy. So I have to add the rest energy to that, because now the total mechanical energy includes this new energy that I just discovered I didn't realize was there. Well, this total energy then is equal to the kinetic energy, which is gamma m naught c squared minus m naught c squared plus the rest energy, which is m naught c squared. M naught c squared minus m naught c squared, that goes away. And I'm left with the total mechanical energy of the system being equal to gamma m naught c squared. But recall that gamma times m naught is equal to m. And so my final result for the total mechanical energy is that that energy is m c squared. The total relativistic energy. Doesn't matter. It did. It did.
I have a question. For E naught, why give it a negative? Or have E naught equals rest energy? Why give it a negative?
Added it to the other side.
No, I'm just saying that this quantity here, which is being subtracted here, is the rest energy. Right? Well, this obviously needs quite a bit of follow-up because it is a mind-blowing result. Gamma didn't disappear because gamma m naught is m. So in this case, you're already way ahead of most people who see this equation. Many people see this equation and they see the m in it and they think, well, that's mass. It's not. It's not mass. It's the relativistic mass, which is a name that I kind of give it so that I can have something to say. It's the relativistic mass. It's not the mass that you get when you put the thing on a pan balance. No. Now the question was just asked, so this is what Einstein did. No, I cheated because I already knew what the answer was and I already knew about the natural behavior, which Einstein did not know. Einstein's approach was different. And I said a thing that is really not a good idea, and I'm going to correct it now. Works beautifully and is basically equivalent, but I did a very non-physicist thing in this presentation. I'll tell you what it is. I implied very, very strongly, in fact, I said outright, that the mass is velocity dependent. There's no way to refute that claim because I do an experiment and I find that when I make measurements of the mass, that the mass is larger and the object moves by me with a velocity v. It's undeniable. This is not the view our modern view of interpretation of this particular facet of relativity. Our modern view is it is not the mass of the object that increases. The mass is the mass is the mass all the time, which is a very satisfying thing. That it's the measurement of the mass that changes because, brace yourself, in a sense, the energy itself has inertia. Energy contributes to the mass. So when a particle is at rest and has no energy associated with its motion, it has only its rest mass. But when it moves along with a velocity v, it has an extra unction of inertia that is due to the energy that it has with its motion. Do you see? This relationship, E equals mc squared, is often referred to as mass-energy equivalence. That mass and energy are equivalent quantities in the universe. And that is true. That's what it expresses. But then it sort of goes off the rail when we talk about electron-positron annihilation. I have an electron and an antimatter electron. They come together and they form a whole bunch of gamma ray photons, energy. The mass is converted completely into energy. So people get the idea that what this equation says is that you can convert mass into energy and back and forth. That is a very, very limited view of what this equation actually says. I'll refer you to something that I don't know if you actually learned in your chemistry. But in order to form a helium atom, I need 2 protons to form the nucleus. When particles bond together that way, the potential energy of the bond is negative. So there's negative energy associated with bonding, and this is a subject that we're going to come back to quite a bit. The mass of the combination is less than the mass of the individual parts. I don't know whether that becomes an issue in chemistry. It's certainly not an issue for chemical reactions, but But when talking about the behavior of nuclei and the behavior of atoms, if I take an atom, which is bound together by a negative potential energy, and measure its mass, and then break it apart into all those pieces and measure the pieces individually, the pieces have a greater total mass than the combination, because the negative potential energy is effectively negative mass. It has a negative effect on the measure of the inertia. You see, the universe ultimately is all about how we measure things. We don't live in the universe. We live in the observed universe. We live in the observable universe. We live in the universe of what we can detect and measure with our scientific instruments. So inertia, no matter what its ultimate reality, is a measurement that we make. And that measurement turns out to be much more sophisticated than we ever imagined. So this kinetic energy, which is gamma m naught c squared minus m naught c squared, is inappropriate. That is the incorrect kinetic energy. So why have we gone about doing 1/2 mv squared all this time being wrong? Well, the speed of light is so enormously large that this effect has never even been detectable until we got to a point where our technology advanced to the point where we could make measurements to verify that this is true. By the way, this is so true. It's really, really quite spectacular. But I want to make a point about the kinetic energy at the end, and I've run out of space here at the bottom of the board. My goodness, Karen, what am I going to do? So the kinetic energy is equal to gamma m naught c squared minus m naught c squared. Yeah, what are you going to do? Oh, thanks. So you have a lot of skill at it, you're saying. You're the good choice to go at it again. K equals gamma m naught c squared. Let me insert the gamma again so that my kinetic energy is in fact equal to 1 minus v squared over c squared to the negative 1/2 power m naught c squared minus m naught c squared. So all I've done is reinserted gamma so I can see the full thing. Well, there's a theorem that I would so much hope that you young, clever people with your maths are aware of, which is called the binomial theorem. The binomial theorem states that if I have 1 plus or minus x raised to the n power, that's approximately equal to 1 plus or minus n times x plus or minus some higher order terms. That's the binomial expansion. It's precise if x is very small compared to 1. Well, it doesn't get better than this. V squared over c squared at slow speeds, 10 meters per second, divided by 9 times 10 to the 18th, right? Yeah, 9 times 10 to the 18th, fantastically small. So this is a very good approximation. So I'll make that substitution into my kinetic energy here, and I'll see what I get. I get that the kinetic energy is equal to, what's this going to be? Well, I get 1 out in front. I get a 1 plus the exponent. Well, the exponent is negative 1/2 multiplied by x, which in this case, x is v squared over c squared, right? That's my expansion of that. M naught c squared minus m naught c squared. Well, look what happens. When I multiply this m naught c squared through, I'm going to get an m naught c squared here at the beginning of my kinetic energy, which is subtracting m naught c squared. That goes away. So I end up with my kinetic energy being equal to, yeah, pardon me, I am, thank you. Oh, that's a shame, isn't it? Oh, well, what can you do? What I'm left with is 1/2, don't yell at me, 1/2 v squared over c squared times m naught c squared, and the c squareds cancel. So what I'm left with is the kinetic energy is in fact equal to 1/2 m naught v squared. Wait. You're going to yell at me and say I ate the negative sign. You know damn well I did. I cheated you. It was negative in the first place. So that is in fact positive, and that turns out positive, and there you go. So at slow speeds, the kinetic energy is in fact equal to 1/2 mv squared, 1/2 m naught v squared. The rest mass and the traditional speed squared. I think one of the things that you understand about the magnitude of this discovery. As soon as Albert Einstein realized that this rest energy existed, physicists went about trying to figure out how to release it. A couple of things were realized. One, this is why it's possible for the sun to produce the fantastic energy output that it does that makes life on Earth possible. This amount of energy. It's a spectacular amount of energy. It's also the way that we figured out that we can make nuclear weapons, converting the mass energy into electromagnetic radiation in a fraction of a second and destroying cities. But if we treat that with some maturity, we can also build power plants. Ultimately, all of our nuclear energy will come from fusion. Once we figure that out, a lot of effort required on your part to accomplish that. But for the time being, there it is for your entertainment, the mass energy relation.